Yeah, so I'm going to talk about very briefly, half an hour at most, on these two kind of complex topics. RAN, disaggregated RAN is a complex topic. Energy savings is a complex topic as well. And I decided to use disaggregated RAN because I don't really know what to call it. There are so many names: Open RANs, Cloud RANs, vRANs, O-RANs, all these things. But I will very quickly touch that and touch what Red Hat does in disaggregated base station. Maybe that's the best thing to say. So this is what I'm gonna talk about today. These 4 topics: RAN models, as I said, a little bit on which domains in telco network we work from power savings or energy efficiency point of view. A little bit a small example, or one example of our partner in energy savings domain, Intracom Telecom, and then few open source projects where we are working on or what we are following, whether they become live or not, and which ones to incorporate into our supported product. So let's start with the RAN, well-known thing. So 2 things happened a few years ago. The left-hand side is the disaggregation of the base station, disaggregating the base station into basically three entities, as we all know: radio unit, distributed unit, and centralized unit. And then O-RAN Alliance came on board and started to cloudify part of the disaggregated RAN, as we know. And that's, of course, where we play in as a software company. So we typically, or we do support 3 different models of this disaggregated RAN. This first one is, we can call it vRAN, we can call it Cloud RAN, people call it something else, but this is not Open RAN, this is one RAN vendor solution, all RU, DU, CU from the same vendor. There is a legacy interface between RU and DU, so you cannot mix and match radio units. But we do support that if somebody wants to build, some RAN vendor wants to build something like this. That's okay for us, and we do have these projects going on. Now, since we are an open company, open source company, and open company in all ways, we do always support and encourage people to use open interfaces. So I add here the O-RAN Alliance front haul, open front haul, and this we can now call Open RAN. It's still not O-RAN Alliance compliant, but this we can call O-RAN, Open RAN. As I said, we always support open interfaces, and we encourage people to use those. These particular open interfaces on this diagram are not in our domain anyway. So it is RAN vendors' domain to comply to these open interfaces in their RAN workloads. Again, RU, DU, and CU. But we still support that, and we encourage people to do that and use those and build the ecosystem around these. But again, our position is the same. You know, hosting DU and CU workloads in this domain, in this model, like in previous one. Now, we do not play in radio unit. There's no Red Hat technology in anybody's radio unit at this point. Is that going to happen someday? Nobody knows. When talking to the RAN vendors, they are very reluctant to give information on the internals of the radio unit. It's kind of a state secret for those people, which I understand. It is a price-sensitive, cost-sensitive thing, and I've been doing very closed RANs myself in Nokia, Samsung, and Huawei previously. So radio unit is a state secret. It's understandable. Now the third model we support, it's now this complex model which really does not exist yet as of today, which is O-RAN Alliance compliant RAN. Everybody have their own diagrams on O-RAN Alliance model, and this is my version of that. So again, in this model, we host the same things, DU and CU, but we also host or can host near real-time RIC and SMO, and we do have this. We have certification. For example, Juniper RIC is running on OpenShift, Red Hat OpenShift, Nokia RIC as well, and Mavenir and some others. So we strictly are a platform company, but also automation and management tool company, which I don't have in these cases. So these models already kind of give indication of what we can do from energy efficiency and power savings point of view. Again, no access to RU, but the other places. So the platform, software platform is abstracting the underlying hardware from the workloads. So we need to fiddle with the hardware and utilize all the power or energy efficiency features on the underlying hardware platform, whether it's x86 or ARM or something else. So that's what we do. And then a big kind of a deployment model, a diagram on these RAN things. Again, we are not the RAN company, but we need to support also, these models, hosting DU and CU in these different or various places, like completely distributed RAN, which is the upper part. Everything still on the cell site might not be optimal thing to do, but we need to support that, and potentially DU, CU running even on the same physical server in that case. Or two servers, it doesn't matter, both work. And from power savings point of view, the only thing we can do for the RAN in the distributed model is to work closely with the workloads or workload vendors and optimize execution and scheduling and placement of the workloads within that within the cell site. Then the fully centralized RAN, where only RU is left to the cell site. Again, we have nothing to do on the cell site in this model, but we again do the same things on DU and CU when they are centralized. And in this centralized model, there is of course a pooling effect available. So we can pool DUs and RUs, which is another contributor to energy efficiency or power savings. Now, this is the whole mobile network or example or diagram, graphic of the mobile network, and based on the reference 2, which is an Ericsson paper, 75% of energy goes to radio access network. But we need to keep in mind that within that 75%, majority goes to radio units. So optimizing the energy savings, power savings on radio unit is extremely important. But again, it's outside of what we can do. It's more like radio vendors' thing to do, or X-apps developers' thing to optimize. Now, we have divided this power efficiency and sustainability or energy efficiency into these four different domains. So we have a node level, which is a physical server, which I will talk a bit more later. Then we have a cluster level, which is a bunch of servers forming or deploying a logical cluster having different, as we call it, worker nodes, having workloads, and the management nodes. So that's a cluster. And then, of course, system level, which is the whole thing, whole network. And finally, the domain level, which is kind of a RAN or core network or IT domain or things like that. And as I said, we are managing the lowest layers on the stack from managing the hardware, power savings features and options, but also working with the partners to kind of intelligently schedule the workloads to a place where it's, from many perspectives point of view, it's most optimized or optimal placement of that workload. From the energy efficiency point of view, for example, or performance point of view, or security point of view, we need to do that together with partners and their algorithms with which they decide where to place different workloads. So these are the list of the same list: node, cluster, system, and domain, and then features within those domains. And I will touch a little bit more the node level, which is the managing the underlying hardware, more or less. And these are the different things we can, again, depending on the hardware platform's capabilities, if they have these capabilities. Not all hardware platforms have, but if these features are available on hardware level, our platform, whether it's a virtualization platform or mostly nowadays container platform, we can control these different things, heat control, frequency scaling, voltage, clocks, and specifically the states, which is the kind of a power efficiency related feature in CPUs. And nowadays, luckily, the multi-core CPU, in multi-core CPU environment, we can manipulate the CPU per core, so we can turn off, core by core, or use lower frequency core by core, which is excellent. That wasn't the case some years ago, but now things always develop, and we can do that. So this is very quickly getting highly technically detailed, so I'm not going to go through all these configuration files in Kubernetes environment, but the point of this diagram or this graphic is very important, and the point is that in the multi-core CPU environment we can partition the multi-core CPU into different domains. So I have this green domain on left-hand side, which we can place pretty much any workload. The workload can be doing pretty much whatever, and it's not the critical workload from performance point of view or some other point of view. So on the green side, we can really manipulate these B and C states to reduce the power consumption. Now the red side, the right-hand side, that is part of the CPU, few cores, how many? 5 cores, 6 cores in this case, where the workload is very critical, like distributed unit workload, where we need to provide a real-time execution environment to be able to manage the timing and synchronization chain using the precision time protocol. So on the red side, we cannot use states, these P states, and we cannot manipulate these states because then the performance characteristics of that bunch of cores will be different, and the workload might not even run, or it might run, but it might not run correctly. So we could lose, for example, synchronization with the radio unit. So we do not do that. But luckily, the platform system can partition the multi-core CPU into these 2 different partitions. It can be even more partitions if somebody figures out that there needs to be something even different. But this is the important thing to do. And this model also is important if you want to have distributed unit and centralized unit workload on the same physical server. So the centralized unit would go to green side and the distributed unit again to the red side. It's highly important. Now this is one example of open source project related to energy efficiency or power consumption. It's called Kepler, and Red Hat founded this project some time ago, and it got a lot of attraction in the industry, and other companies started to contribute to Kepler. So Kepler is not really managing the power consumption, but it's a reporting tool, collecting metrics and reporting how the power is used and how it is distributed in the system. Very important open source project in that way. Then I have a kind of complex diagram from our partner, Infracom Telecom, which we presented this demo in Mobile World Congress this year, and we have at our booth, we have a video on iPad running the same demo we had on Mobile World Congress on what really happens with Intracom and Red Hat. So Intracom, and this is a UPF example, by the way, not radio access network, but UPF, which is another sensitive network function. So Intracom software is running on OpenShift and doing its magic with their AI and ML algorithms to optimize the power consumption of UPF and not violating the performance characteristics. So they run on OpenShift, and they give Intracom workload is giving instructions to underlying container platform Red Hat OpenShift to do things and stuff. So we don't do this magic, but we just get these instructions from the workload to do different things. Now, a few more examples of energy efficiency related open source projects, which we are looking at, and we are contributing to some extent, but we haven't, just to make sure, we haven't made any decision to downstream these and put them into our products yet. That might happen or might not happen, we don't know. But and there are others. These are just few examples. There are quite a few open source projects related to sustainability or energy efficiency. Many of those open source projects, which is typical, are overlapping partially or even completely, and industry is looking which of those overlapping projects will become successful, and then the other one will die. That's a typical way how it happens. And maybe this is a appropriate slide just to mention how we work with our product. So we call our development model open source upstream first, which means that all code we develop directly in open source project out there together with our customers and partners and competitors, even mainly with competitors, to create the code. And then when the code is ready, or there's a community release, then we take the community release and incorporate that into our supported products. And why we call it upstream first is very interesting, and it's been a big challenge for us to explain it to service providers during last almost 10 years since the invention of NFV, but also to equipment provider, because if our customer is asking us a new feature into our product, I need this feature, we cannot commit to that ever. I mean, not at that moment. Someday, yes, but not at that moment. What needs to happen first is that we socialize this new feature idea with the open source community leaders, whatever the project might be, OpenStack, Kubernetes. We socialize that feature, and if the open source community leaders agree that, this is a good feature, let's agree that it will be in one of the upcoming community releases. Once that happens, then we can go back to our customer and say that, hey, now I can commit to that feature you requested from me earlier. it's been very difficult for many people to understand that this is how it works. And the other thing, why Red Hat development model is very powerful is that we don't do open source development as it is typically done. So it's typically done in most of the companies that they develop something at home or at the company, and then they start pushing that into open source projects. And it's a very difficult thing to do, and that's why we develop everything directly in the open source project. We don't need to push it anywhere. It's already there. So that was quite a bit on open source, but it's an important topic. Now my last slide is the same diagram as always, just pointing out that it's not just radio access network where we do this energy efficiency magic or other magic. It's whole network, throughout the whole network, except radio unit, one more time. But the whole network, and then of course extending to OSS, BSS, and any IT application which might use OpenShift platforms. And when you accumulate all the energy savings throughout the network, then it starts to become important, more important. So that's about it.
Thank you. Interesting.
Thank you.
Very interesting. Immediately you need to go into the demo. Thank you.
Hi. Thank you for the presentation. As a brownfield operator, to deploy Open RAN, there are like number of challenges, right? So one is Open RAN need to be parity with performance, parity with TCO, and thirdly parity with energy, and fourthly maybe differentiate and introduce innovation. So I see that sometimes you may have to compromise on one to get the other. It might be the case. The question to you is in terms of energy. Now, if I look at Open RAN architecture, a lot of things will change, right? So you need to change the server architecture, the acceleration, the sync, then the front haul, all of this could change. And when I try to really understand the impact on energy, a lot of those variables can change the picture quite dramatically. Like for example, depending on the acceleration you select, it might be a completely different energy profile. And one of the, I suppose, the thinking schools of thought might be that you may have to compromise on energy, but the XApps or the applications that run on it can bring the energy down. I just want to ask you, is that your view as well? Because because all of the changes that are going to happen with Open RAN, your energy profile might increase, but because of the applications and the intelligence behind it, that's what really brings the energy down compared to our standard classical RAN architecture. Or is that a different view?
So I rather not answer that question directly because we are not a RAN vendor and we don't really deal with whether it's difficult to do RAN in brownfield or not. That's not our business. We are just, as I tried to clearly explain, we just host workloads from core to RAN, and it's RAN people's or the service provider or maybe equipment providers' problem more or less to deal with those issues you mentioned. We just try to make things easier from automation point of view and execution point of view and energy efficiency point of view. But again, we are not the RAN vendor.
Anyone else?
Yeah, so one question. So in the last chipsets that Intel have put out, and I guess AMD as well, but I'm probably less familiar with them. And actually over the last couple of years, there's been a huge amount of power efficiency in those chipsets that pretty much nobody's doing anything with. I just want to, is what your position in here is the fact that you've done the work to make that work? So like, for example, in the last is it Sierra Ridge? I can't remember which one it is, but there is a massive amount of power management capability that literally most people don't even know exists. And the Intel guys are getting very frustrated because they build all this stuff that no one uses. And I'm just trying to qualify, is what you're doing in OpenShift enabling that and enabling it from a workload management point of view?
Yeah, we do all that. And I completely agree with you that, these modern chipsets or hardware platforms, they do have a lot of features nobody have ever heard about. And it's fair to say that, even ourselves, we are kind of early phases on this journey, this sustainability, energy efficiency, power management journey. And we have learned a lot during last 10 to 12 months to really dig into the details of different x86 chipsets and ARMs and others, that we have found out that, we can do that, we can do that. So, and our journey is nowhere near to be complete yet. It is continuing, and it's really interesting why, or how is it possible that there are so many hidden features? Not hidden, but features that people just don't know.
Well, it wasn't a priority, so that's why. But I think it's really great that you guys are doing that, but also interesting that in a software world, inverted commas, we still need to know a lot about the hardware, right?
Well, that's a point. I tried to make a point that our job, building the platforms, our job is to abstract the hardware as much as we ever can. But while doing that, we need to master hardware better than anybody else has to do. And one thing I forgot to mention, and I forgot to even put the slide in, is the hardware accelerators on distributed unit. And there are so many of those. Somebody likes, Lucasite model, somebody likes inline model, and even those hardware accelerators, they do have their own power management and energy efficiency features, which we all also work on. But I didn't have it here. Of course, kind of, not sadly, but there are so many hardware accelerators, and our RAN partners pick what they pick, and they favor what they favor, and we have to integrate pretty much all of those into OpenShift, although we don't need the hardware acceleration features ourselves, but we need to integrate them to allow this DU workload access to the hardware accelerators.
Yeah, one question. So I agree that sustainability is important, and it needs to happen in an autonomous way. You cannot observe monitors and then switch off CPUs manually. And my question is related to these closed loops, Can you do sustainability just purely based on software-defined algorithms that execute on, let's say, predictive analytics? Or do you really need like AI-driven neural networks that you need to train in order to get the most optimum result out of it?
So we can do closed loop already now on energy savings portion, but it's, as I said, we are early on this journey, and it's probably not even close to optimal yet. But the Intracom example I gave, and what we have the video on our booth, they use, on my understanding, very intelligent AI ML algorithms in a closed loop way together with OpenShift to do that. What their algorithms are doing, no idea, that's their property, but it seems to work well, at least in this existing UPF model, user plane function model, probably other models as well.